Okay, so this lecture is going to be about Gauss's law. So Gauss's law, here it is, looks very intimidating, and we'll kind of break down what all this stuff is in this lecture and the lectures to come. Um, but just for full disclosure, Gauss's law does not contain any more or any less information than Coulomb's law. Okay, so it's just a different way to formulate um, Gauss's law is just a different way to formulate the Coulomb's law we've been talking about since the beginning of the course. It's just that it's so wildly different in how it approaches things that it's an extra tool that will get us um, uh, some calculations done much more easily than we could before, or maybe would have been close to impossible, or just really difficult to do before. My analogy would be like if you have a city and there's two maps of the city. One is all the bus lines and one is all the subway lines. Um, of course, the city only has so many different places you can go. It's not like, there will be, it's a different city that we're talking about. It's just we're talking about ways to get from place to place. So sometimes the bus might get you there much quicker between points A and B, and sometimes a subway might get you much quicker between points A and B. The beginning A and the destination B, the journey is the same, but we just want different options in terms of how to connect those. One of the things I already mentioned in earlier videos is that doing direct integration like we did on homework number 2, doing that's already tough enough in 1 and 2D, so we did not touch any 3D charge distributions at all in homework number 2. But Gauss's law will actually be the only tool we have to attack 3D charge distributions. It can't just do all of them super easy, but if there's certain symmetry, then we can tackle the 3D charge distributions really easily. So Gauss's law is really a law, just to kind of give you a preview. It can't just do just about anything easily. But if there are certain symmetries involved, then Gauss's law is really good. And so that's what we tend to use it for. It's not that it's not true in other cases. It's just that it's really difficult also to still do the calculation. So some really crazy charge distributions, there's just no easy way to do them. Whether you're talking about integration from homework 2 or Gauss's law here from this homework, there's just no easy way. So this is just an extra tool. It's not something that will get you everything you want anytime you want it, but it does give us another tool to operate with. We're going to have to break this down piece by piece. This is the closed integral of E dot dA equals phi sub E equals Q enclosed over epsilon naught. Some familiar pieces and some completely new. And just to kind of get started on this, we're going to take off our physics hats for the moment, and we're just going to become wildlife biologists for a second. So I'm going to draw here a nice stream and some fish swimming in it. There's a couple fish. And let's say we're interested in what's the health of this fish population. Okay, maybe this is an endangered species of fish or something. We want to go up to some mountain stream and we want to be able to figure out, are these fish doing better or worse over the various seasons? Is their population rebounding? Are they going extinct? What's going on? Now, when biologists do this, they can't literally catch every single fish that exists. That's obviously not realistic. They're just going in and sampling. And so let's pretend here that we have, say, some sort of like hula hoop type ring like this, and the fish can swim right through it, but this has some sort of counting mechanism on it. So when a fish swims through it, it just goes blip, and it counts it and says, okay, one fish swam through. And so what you're going to do is you're going to put that in there for a certain amount of time. You're going to measure how many counts you get, and you're going to use that in some sense to gauge how the fish are doing. So here's my formula that I'm going to suggest. There's some fish density, right? So there's some underlying fish population that is there that's impossible to directly measure. You can't count every fish, but there's some underlying fish density. And I'm going to do is I'm going to multiply that by the area of my catcher, or I guess I call it my area of my counter. I don't want to actually harm the fish. I just want them to swim through and count them. And if I multiply those two together, then I'm going to get some measure of the fish that I've counted, right? So this thing on the left-hand side is actually my measurable. Okay, how many fish did I count? And that's going to be the proxy for this underlying fish density that I don't know. Essentially, what I want to do is I don't really want my counter to be much of this situation. So what I'm going to do is I'm going to leave my counter as a constant. I'm going to, of course, lug up the same counter up there to the mountain stream year after year. And then let's say I count more fish, so that is increased, then I'm going to assume that's because the fish density itself is increased. So taking the counter out of the situation, then these two are going to kind of track together. And so if I see that I count more fish in a given year, I'm going to assume the fish population is doing better. I'm going to assume there are more fish in there. And likewise, if I count less fish every year, then I'm going to assume that the fish population is not doing so well. So these two things kind of correlate to each other. This is, of course, you can hopefully see why you'd want to use the exact same area of counter every single season. If, 1 year you get sick and you can't go up there, and you send up your friend to do the counting, and they say, great news, I counted so many fish. And they tell you, actually, I used a giant counter. This thing was massive, right? Something huge, okay? Well, then that doesn't really mean anything, okay? Maybe the fish density was totally constant, okay? But because you just suddenly used a much larger counter, you're going to count more fish, okay? It's not that there are more fish in there. It's just that now you're just counting more fish because the counter is bigger. So if your hoop is bigger here, then maybe some fish that would have gone above or below your old one and you wouldn't have counted them, now you're counting them all. So you can hopefully see why it's important then in this particular application, why you want to leave the counter to have an area that's constant. And you can hopefully also see why I chose to multiply them, because both of these things being increased is going to lead to an increase in the count. So if either there are more fish in there or the area of the counting thing itself is bigger, of course, then you're going to miss less of them. And so both the reasons the fish that you're going to count is more. There's another possibility. Maybe another year you go up and you count no fish whatsoever, and you think, oh my God, have they gone extinct? Well, maybe your hoop fell over like this, and that's why you got no count, okay? So the fish just kind of missed it. They didn't go through. Now, obviously, a fish might be able to like swim vertically and kind of still go through there or something like that. We're going to discount that possibility. You'll have to forgive me. This analogy is not perfect, but assuming that the fish can only swim sideways, if your hoop or your ring that you're using to count them with is in the wrong orientation, no matter how many fish there are, you aren't going to catch any, or you're not going to count any. So hopefully you bear with me here on the analogy part. Instead of fish, we're counting field, okay? So instead of the fish swimming to the right here, we're counting field that goes to the right. And then we are still going to put some sort of area in here to count them. And that's essentially sampling the field line. Not all the field is going to go through there, but we're essentially trying to count how much field does pierce this area. So fish density, instead of fish density, it's going to be field line density, E. The area of the counter, I'm just going to call A. That's the area of your surface there. And the thing that I'm counting here is flux. Okay, so flux is a sort of a way of sampling a field by putting an area into that field and counting how much field goes through it. So essentially, there is a big kind of relationship between flux and field itself. Anytime that you have a field, you can talk about the flux through a certain area that you stick in there. So you can have electric field and you can talk about electric flux. That's what we'll do for the moment. Toward the end of the course, we'll talk about magnetic field, and you can have a magnetic flux. You can even talk about gravitational field, and then you can talk about gravitational flux. So flux and field are they're kind of tied together. They're two very related quantities. Anytime you have a field in a region, you might want to sample it with an area, and that quantity we call flux. Now, this formula does need some refinement, but it's already got enough correct about it that we can actually get the units of it. The units of flux are going to be the units of field times the units of area. Electric field, we have two choices. I'll do newtons per coulomb, which was the earlier form of units. And then, of course, area in SI units is measured in square meters. So that's 1 unit of flux, newtons per coulomb square meters. We also saw in homework 3 with voltage that you can also express electric field as voltage per meter. So we talked about that the electric field is measuring how rapidly the voltage changes with distance. And if you put that in there, you do get a little bit of cancellation, meters squared, meters here. So another SI unit that's completely equivalent is volts meters. So there are two different SI units you'll see for flux, just the same way as there are two SI units you'll see for field itself, newtons per coulomb or volts per meter. If you write it like this, please make sure to write it volts times meters, because if you write it the other way, MV, it's going to look like millivolts, and it's not millivolts. This is meter volts. That's, by the way, the same reason in physics 1, when you wrote torque, the units of torque were Newton meters. The reason you don't write it meter newtons is because it makes it look like millinewtons. So it's kind of nice whenever the meters by itself is part of the unit, you put it later so that you don't mistake it for a prefix of milli. Okay, so the units aside, the couple things we need to do to this to make it bells and whistles is that we haven't yet accounted for the fact that if the catcher is in the wrong orientation, like so, then we say that there's no flux at all. So in fact, this area would be oriented to catch maximum flux, and here the flux would be 0. So let me show you how to do that. What we need to do is define a way to talk about how the area is oriented in 3D space. And for that, we have a tool. Let me draw the area here. The tool we have is called the normal vector. So it is a unit vector, hence the hat. Okay, so n hat is called the normal vector. It is a unit vector. And its definition, as it might be suggested by the word normal is another word for perpendicular. For instance, in physics 1, you talk about the normal force. This is not to be mistaken with normal force. This is not a force. This is a vector, which we've defined. And the definition is that it's perpendicular to the entire plane of the area. Okay, so this is perpendicular to the plane that the area lies in. Okay, so let me try to show you this. Let's say I have some area. So the normal vector is like this. So it's perpendicular to the entire area, okay? And that's how it's defined, okay? And the reason, of course, that it's very handy to define it like this is because with that single arrow, if I say the normal vector points like this, then, of course, without any further information, you know in 3D space, there's an area that's in this plane. If I tell you the normal vector points like this, okay, then you know that there's an area like this. So it's a very convenient way with a single arrow to talk about one slice, one plane of 3D space and talk about where in 3D space that area is actually sitting. So this is the entire area, and then this is the normal vector that is perpendicular to that whole thing. We go a little bit further and we actually package up these two together. We define an area vector. The area vector is just carrying these two pieces of information around together. It is carrying around the area, how big is the area of the catcher, and it carries around with it the orientation that it has in space as given by the normal vector. So what that actually allows us to do is it allows us to turn the definition of flux into a dot product. And let me write it over here. It allows us to turn the definition of flux. Flux is going to be a scalar, a number that is formed from two vectors, the electric field vector and the area vector. And let me just remind you, there's a couple different ways to do a dot product. One is component-wise. We're not going to use that too much in this class, if at all, but that would be EX AX plus EY AY plus EZ AZ, and we do have to do it in 3D here, but we're not going to need that at all. We're going to do the other definition, which I'm sure you remember from Physics 1. There were lots of quantities that were dot products. Work was a dot product. So we take the magnitude of E, magnitude of A, times the cosine of the angle between the vectors. Okay? And of course, remember that the A vector just gets its direction from the normal vector. So we're really talking here about the angle between E and n hat. Okay? So you can write it either way if you like, but of course, more properly when you're writing it, you want to write it as magnitude of one vector, magnitude of the other, cosine of the angle between those two vectors. So it's worth a bit of review on the dot product. Okay, used it in Physics 1 a bit, but always worth reviewing. So the dot product, the angle between two vectors, has a maximum range. It has a minimum of 0 and a maximum of 180. Okay, and when the angle is 0, then the cosine of 0 is plus 1, and so your flux will be plus EA. Okay, and so if that angle is somewhere greater than 0, but still greater than or equal to 0, but less than 90, then the cosine of an angle like that is going to be positive. So you will get positive flux. That's when the electric field and area are more in the same direction than not. We get a positive flux. Flux is positive. Sorry, I ran off the end of the page there. Flux is positive. If the angle is 90, cosine of 90 is 0, we get 0 flux. And if the angle is bigger than 90, and of course the maximum it can be up to and including 180, then the cosine of such an angle is negative. That is when the two vectors point more oppositely, and then the flux will be negative. And finally, if the maximum angle they can make to each other is 180, then cosine of 180 is -1, and we get that the flux is minus EA. Okay, so that's just a review of the math of the dot product. I've just sort of used E and A as vectors without really talking about their physical meaning, but let's go back and double check over here if this makes sense. So my first case, right here, my normal vector is like so. You can see that the angle between E and n hat is 0, so this theta is 0. And so my original formula EA, well, that was totally fine because cosine of 0 is, of course, +1, okay? So that one was just fine. Over here, now my normal vector, let's say it's upward. Sorry, this is in my way, but normal vector is up, sorry, went out of frame there for a second. So the normal vector is like this, and the electric field being still to the right, which I can draw in here. Well, now that's a 90-degree angle, and theta, what we said was when the angle between them is 90, cosine 90 is 0, the flux is 0. So that sort of corresponds with the fact that we said you're not going to get any flux when the catcher is turned the wrong way. And so um, the uh, um, the one thing that you might point out, and you'd be very right to do so, is if you had a catcher that was like that, okay, so we had a catch, we had the field going to the right, the catcher's going like that. How do I know whether to pick n hat to be this way or this way, right? They both meet the definition of being perpendicular to the plane of the area, all right? How do you know whether to go perpendicularly out this way or this way? Well, there's no right or wrong answer. You can choose n hat to be this, or let me do it in a different color. You can choose it to be that way. Okay, so which do you choose? There's no right answer. So if we have an area like this, which I'll call an open area, and what I mean by open area is it's just an area out in space. This side is outside, open to the environment. This side is open to the environment. It'll be easy to distinguish this from a closed area, which we'll get to in just a minute. But if an open area, there is going to be two possible choices for n hat. And what that actually means is that there are going to be two possible choices for the sign of the flux. Okay. For instance, with the blue choice, the angle would be 0 degrees, okay? That n hat is pointing the same direction as the field, and the flux would be plus EA, whereas if I chose n hat to be the red one, well, that makes a 180-degree angle with the field, and that is going to be, flux is minus EA. So you can see they both have the same number. It's just that one has a plus and one has a minus, and that will apply in any instance. Essentially, if you have, if you have something that's tilted weirdly like this, then the normal vector out this side goes like this, the normal vector on this side goes like this, and the field goes like this. So this angle right here, that's what I'd use if I were calculating the flux with the blue normal. And then here, this is the angle I'd use calculating it with the red normal. So the angle, remember, if you don't recall, when you are measuring the angle between two vectors, you have to measure the angle when they're placed tail to tail, okay? So that can range from 0 to 180. So remember to go tail to tail if you don't remember that. This is not to be confused with when you're putting vectors head to tail. For vector addition, we're not adding these vectors, and these vectors aren't even addable. You can't add two unlike quantities. You can't add an electric field vector to an area vector. It doesn't make any more than saying 1 meter plus 1 second equals 2. It doesn't. You can't add things that are different units. So these are placed tail to tail, and you measure the shortest angle between them when they're placed tail to tail, maximum 0, or minimum of 0, maximum 180. And here you can see that the blue angle and the red angle are supplementary. So supplementary meaning that the two angles add up to 180. You may remember complementary angles add up to 90, but we're talking about the blue angle, theta, and the red angle, theta, actually add up to 180 degrees. And it turns out the cosine of an angle and the cosine of its supplement are basically always going to be opposite signed, so otherwise equal, but have a differing sign. So cosine of the blue angle is going to be the negative of the cosine of the red angle. And so, so what do we do with this? It's not really a problem, but just remember, if you're calculating flux like this, there's two perfectly valid possible choices of normal vector, which means there are two totally fine possible choices for the sign of the flux. Neither is right or wrong. And so if you are doing something like this, you're going to either have to be given which of the two normals to use, or the person who's asking better be okay with the difference in the sign of the flux, okay? And there's no right or wrong answer. So that's a little bit about sign of flux, but If just as a general kind of summary of flux, so the things that are going to depend, the flux depends on just kind of conceptually, is first of all, what are you counting? So the electric field strength itself is going to affect it. The larger the electric field strength, the larger the flux will be. The second question is, what are you counting with? What are you counting with? Counting with. So the area matters. Okay, so if you're counting with a bigger area, you'll get a larger flux. And of course, the counter orientation matters too, theta. No matter how much field strength you have, no matter how big the area is that you're sampling with, if the orientation is wrong, if you have a situation like this, the flux is still nothing, okay? So that's kind of the concepts of flux, and that all goes right hand in hand with the formula for flux. You can see all the ingredients, E, A, and theta, right? Okay, so that's just kind of a general introduction to flux. And there's one more thing that we need to mention about flux. Sometimes this formula here is not quite so nice. For example, the general case, let's say you have a sort of area to catch again with, and I don't know why, but I'm not drawing it as a circle area. I'm drawing it as a plane here. But let's suppose that you run into this situation. Maybe the electric field up here is strong and points that way, and the electric field like right there is weaker and points that way. So now the electric field has different things going on at different parts of this area, okay? Now if you look back at the original formula, I guess I'll just rewrite it here. So this E dot A just sort of assumes that the electric field has a certain well-defined relationship with the entire area, okay? So it essentially assumes that the electric field has a constant strength and direction relative to the entire area. And that's clearly not the case here. So what do? This is where we do a little bit of calculus. So instead of just having one big area, we're going to slot it, we're going to change it, and we're going to break it up into a bunch of different areas. So we essentially just kind of take this and make the whole area out of little tiny pieces. And as you can probably guess, these little tiny areas are going to be called dA. And each of these areas is going to have its own local normal. So that one might look like that. That one might look like that. Okay, remember that has to be perpendicular. And then we can make them all little areas, dA vector, okay? So what you have to kind of do is on each part of the thing, each part of this, you have to take the local electric field, which is now a function, and dot it with the small little dA that is at that local location. And by the way, I'm kind of blaming it on the electric field because the electric field might be stronger and in a different direction over here. But another reason why this might happen is because maybe your area itself is kind of curved. So it's like a billowing sheet or something like that. And so the dA down here, maybe the electric field is exactly the same as up here. So let me try to draw the same length of arrow and the same direction. But now, because my area itself is curved, now the normal here is changed orientation. Remember, it has to stay perpendicular to the area. And so that might be another reason why the relationship is not so nice. So if you do that, you take the local electric field, whatever it's doing, with the local dA, whatever it's doing, okay? And here, again, we might have the situation where we either have for either non-uniform fields, okay? So the field strength itself might be changing in strength and direction. For non-uniform fields, areas that curved, or both, of course, you will need to use this new form we come up with. And then this, of course, will give us the small contribution to the flux from that particular little square. And then when we integrate all of those, we'll get the flux overall. And so the general formula for flux is integral of E dot dA, okay? And now we're starting to get to something that looks a lot like our original law, okay? So if you look back here, there's your integral of E dot dA equals flux, okay? This little circle here, I'll explain in a second what that's for, but essentially that's the general formula. And that's what makes Gauss's law look so impressive and intimidating. However, let me tell you something, okay? This is an important thing, okay? Important, okay? Okay? We are not going to do any flux integrals in this class. And that is not simply just because I don't want to, give you some tougher problems. I'm sure your calculus, probably calculus 3, I guess. I'm not sure where you see this, but I'm sure that you'll do plenty of integrals like this at some point in your calculus journey. However, we don't need that, okay? If you're integrating something like this, you probably shouldn't be using Gauss's law in the first place, okay? Gauss's law is not generally useful if integration of flux is necessary or needed, I guess I'll say, okay? We will be smart and choose the situation so that the flux being E dot A will work, okay? In other words, it'll be sufficient, okay? So why do I even mention this other stuff? Well, I want to show you that in general, you got to be careful, okay? If you get into a situation like this where you're not choosing an area, you're choosing an area poorly, then you wind up in a situation where you have to do something like this. So we will actually choose a situation to make sure that the electric field is nicely well behaved on this area. So we'll essentially choose a situation where we make sure that the electric field has constant strength and direction relative to the entire area. So that is an art, okay? It's an art in choosing wisely so that you can do this calculation very easily, which means that you have a very relatively straightforward relationship between flux and field, okay? So the flux here will just be EA cosine of theta. And so what we're actually going to do here, this is how Gauss's law works, is that once you have the flux, we want an easy relationship and just get the field. That's our ultimate goal. This is a new way of finding fields. So if you can get the flux and then you have an easy relationship, and it's going to turn out that because you need to choose a situation, the situation needs to be highly symmetric, okay? Otherwise, once you have the flux, you can't really get to the field very easily. And that's our ultimate goal, is this is a new way of calculating fields, okay? So now you sort of understand, hopefully, where's that first page? Here we go. We understand the relationship between flux and field. So we got this part mostly. Now we need to switch gears and talk about the other part. It's going to turn out that flux here is really just a middleman. It's a means to an end. We're going to, ultimately what our goal is with Gauss's law is that it gets us from what's the charge to what's the field that it makes, okay? It's the same as Coulomb's law, right? That's the question we've been asking for a couple homeworks now, right? Given the charge, what field does it make? This is just a midway stopping point, okay? So what I'm going to do next is I'm going to talk about the relationship between flux and charge. And once we do that, we've talked about the relationship between flux and field. We'll talk about the relationship between flux and charge. And this is really just going to be an intermediary stopping point. In fact, after a while, when we write the law, we won't even bother to write this part. We'll just write this equals this, okay? And this is sort of just kind of a midway stopping point during the calculation. So let me go ahead and talk about that relationship. So flux, electric flux is equal to Q enclosed over epsilon naught. Now, before I worry about that constant, I do want to point out that this is essentially just saying that the electric flux is straightforwardly proportional to the charge enclosed, okay? So this, it's hard to prove this exactly, but I'm going to do a highly motivated discussion of why it makes sense, and a little bit later on I'll show you that it exactly reproduces Coulomb's law, and hopefully that's sufficient evidence for you. Now, first of all, before we go any further, we are going to make sure that our surfaces that we're catching with, they're no longer going to be open, they're going to be closed. All right? So, what does that mean? Before, we had an open surface that had both surfaces. I guess I can pull out my example here. This is a rectangle instead of a circle, but it had the area, this side was open to the environment, so is this. But now what we're going to do is we're going to imagine that we have a closed surface. So a closed surface is one, okay, where you actually will take the surface, and as best as I can, I'll go like this, and I'll close it up, okay? So now, this has an inside and an outside, okay? So what this has, I'm gonna try my best to draw that. I can't draw that exact kind of pillow shape that I made with that piece of paper, but imagine now that we had a closed surface. So it has an inside, and an outside. So now, essentially, the surface has trapped some volume inside of it, and then the rest of it, what's on the outside, is the rest of the universe, okay? So what this actually allows us to do is something cool. With an open surface, there is no way to resolve the ambiguity in the two choices of normal. But now there is. You can choose, on this surface, you can choose an outward-facing normal. So it looks like that, let's say. So everywhere on the outside, okay, the normal points, remember, it's always perpendicular to the surface. So there's an outward-facing normal that points from the surface out to the rest of the world. And the other choice would be an inward-facing normal, where the normal to the surface pointed in everywhere. And here's where we, by convention, we choose, and again, this is just a personal choice, we choose, by convention, we choose the outward-facing normal, okay? So the normal that's blue here that points from the surface out to the rest of the world, okay? Now, you can't do that here because they both point to the rest of the world, but when you have a closed surface, you can sort of distinguish the two normals, and we choose, by convention, we choose to the outward-facing normal. So that choice, by the way, is already baked into Gauss's law, and so that's important to realize, okay? So this is already assumed in Gauss's law. Okay, so let me try again. I'm going to try my best to motivate why this makes sense. Let me go ahead and start with a point charge plus Q. And we know what the field looks like for that. The electric field lines, we have chosen them to point radially outward. They start on the charge and emanate out to the rest of the universe. And I'm going to surround this with a surface, and we'll call this a surface area, and that we'll call the Gaussian surface, because it's the surface that we'll use in Gauss's law. On that surface, the outward-facing normals look like this. And what you can see is the electric field lines point outward, the normals point outward. So in fact, the angle between the electric field and the area vectors is going to be definitely less than 90, okay? And so the flux overall is going to be plus, okay? So if you look back over in the dot product review, remember if the angle between the electric field vectors and the normal vectors is less than 90, then the flux will be positive. This is saying that the flux that you are measuring across your surface is directly proportional to the Q enclosed. Well, Q enclosed, of course, is positive. Okay, so we see that when the flux is positive, Q is enclosed is positive. And what I mean by enclosed charge is that there's charge that's trapped inside, right? So enclosed inside my Gaussian surface. So by the way, the outward facing normal is crucial for this because that ensures that when it's a positive charge inside and the electric field lines go outward, that the normal goes outward too, and that makes this that the sign of the flux agrees with the sign of the charge enclosed. If you chose the inward facing normal, then a positive charge would get you all negative flux. So you can see the formula doesn't work, right? Positive charge enclosed, negative flux. You could modify the formula by putting an extra minus sign in there, but let's use Gauss's law as it's used by everybody, where already by convention the outward normal is assumed, okay? We can check out the negative charge, just to kind of bring it home. We learned that a negative charge, we chose that the electric field lines come in from the rest of the universe and terminate on that charge. If we surround this by a Gaussian surface, remember that the outward facing normal is still our choice, and you can see that the angle between the normal vector and the field is going to definitely be greater than 90. In fact, almost close to 180 as I've drawn it here, that's somewhere between 90 and 180. And that is going to mean that the flux is negative, which makes sense because, of course, the charge trapped inside is also negative. So you can see that the flux and Q enclosed, the signs always match. Now, I haven't proven, of course, this formula exactly, but I have sort of motivated why when you have charge inside, you should get some sort of flux measurement, right? Because here, the field lines are all emanating outward. There's no question I'm going to get positive flux here. And here, when the electric field lines are all inward, there's no question that because I have a negative charge inside my surface, I'm going to get a negative flux measurement, right, when I put the counter around the charge. Now, let's do a couple other examples. Let's say that I have a positive charge again, but I'm put my surface over here, okay? So my surface is over here, my counting surface, and here, as you can note, that there is charge, but it's not enclosed. So what would happen here? This field line would not only pass into the surface, but also pass out, like so. And if we drew the normals here to the surface, something like that, you can see that here, when the field line goes in, then that is going to make, it's going to be something more like this, right? Where the angle is greater than 90, and I'm going to get a small negative contribution to my flux. I'll call it d phi is negative. And then over here, when the field line passes back out, then it's going to make a little bit less than 90-degree angle with the normal vector. And then the contribution here is going to be positive. And so you're going to, if the charge is not enclosed, then the field line is going to go both in and out of the surface, and you're going to get both negative and positive flux contributions. It's not like over here, where these field lines essentially originate on this plus charge, so they can only just go out it's a one-way thing, right? They go out once and get counted once. Same thing here, they get counted once on the way through. But when a charge is outside the surface, then the field line will both go in and out, and it'll get counted as negative and positive flux. Now here's my big leap in logic that I'm going to ask you to believe me. If you go ahead and you do this massive, very, very ugly probably need the help of a computer, do this flux integration here. What you're going to find is that the sum of all those negative and positive contributions is 0, okay? And the reason why is that the flux is 0 because there's no enclosed charge, right? There's no charge in there, okay? There might be charge, but we only will get this. What this law says is we're only going to get flux if we actually have charge enclosed inside the surface, and here we don't, okay? So note here, again, I know this is a little bit of a leap in logic. You know, I certainly haven't proved this, but I'm sort of motivating. If you don't have any charge actually living in your surface, inside your Gaussian surface, you're going to get a 0 flux. Now, the electric field certainly isn't 0. I'm not claiming that, okay? The electric field isn't 0 anywhere along the surface. Of course, the electric field for this is going to look like this. The electric field is not 0 in this region. I'm simply saying that because none of it actually lives inside, that I'm going to get 0 flux, okay? This is going to be an important thing to understand later. If you have enough symmetry, then this is a different story. But right now, just because the flux is 0 doesn't mean the field itself is 0. Let me keep doing some examples, so hopefully this makes a lot of sense. So let's do a classic electric dipole. So we have a plus Q and an equal opposite minus Q. It is not the first time we've seen this. We've seen this, I think, since homework 1. And the field lines for this, let me just do an example. They might look like this. I'm not going to do a ton of them, but we sketched this field line before, like so. Let me do a couple more. And one of the important things we talked about in homework 1 is that since they're equal and opposite charges, we should have the same number of field lines connected to each of them. So I drew 1, 2, 3, 4, 5, 6, 7 for this one. There's 1, 2, 3, 4, 5, 6, 7 for this one. And so what that means is, of course, is that the 7 lines that go out of the plus charge all reconnect to the negative one. Now we can go ahead and throw it in our Gaussian surface. It's getting a little bit, a lot going on. So let me go ahead and put that around like this. I'm going to put it around this, and I'll draw a couple normals here, right there maybe. Remember, it always has to be normal to the surface, so on and so forth. Let's leave it there. Over here, it's pretty similar to this last one, so let me refer to that one. So you can see that for every field line that comes out, it pierces the surface going outward. So one's coming out of the plus charge. Those make an angle that's less than 90 with the normal, and so that will be a small positive contribution to the flux. And then over here, let me draw the direction of the local field. That is going to make an angle greater than 90, and so there's going to be a small negative contribution. And I'm asking you to believe me, is that if there's some positive flux, some negative flux, what you end up getting is that the flux overall is 0. And how could I have known that in the first place? Well, going over here, same reason over here. Here I had no enclosed charge whatsoever because there's nothing in there. Here I also have no enclosed charge because plus Q and a minus Q that are equal, my enclosed charge plus Q plus negative Q is still 0, okay? So I don't have any overall charge living inside here, so what Gauss's law tells me is that my flux has to end up being 0, okay? Again, it does not mean, same thing, reasoning over here, I got a flux of 0 because I have no charge enclosed. It does not mean that the field is 0 anywhere. In fact, here the field, in both cases here, the field is non-zero everywhere along the Gaussian surface, okay? So even though the flux is 0, the charge enclosed is 0, either because you have no charge at all or because the charge you do have is all adds up to 0, you'll get no flux. However, the field isn't 0 anywhere on the surface, okay? So, so we'll come back to this later and contrast that with some future stuff. It turns out that there's one missing piece that allows us to jump and say that this is 0 as well. So we'll come back to this a little bit later, okay? Okay, now let me do a counterexample, or one more example here, just to hammer the point home. Let's say I have a plus 2q and a minus q. So very similar charge configuration, two charges, one plus, one minus, but they're not equal anymore. So what's different about this? Well, if I chose to have 1, 2, 3, 4, 5, 6, 7 lines here, let's see, 1, 2, 3, 4, 5. Oh, there's gonna be too many. 7. You get the point here. But if this is twice as much, then if this one gets 7 lines, it's going to need 14. So they can't all leave here and connect here. So some of these I'm going to have to draw 7 more. 1, 2, 3, 4, 5, 6, 7. There are going to have to be 7 more lines here on this one that don't actually connect to this one. And hopefully you can see where I'm going with this. If I draw my Gaussian surface around this, there's no way now that I could get a flux of 0 anymore, because some of these lines that go out don't ever come back in. So over here, every line that left and got positive flux counted came back in and got negative flux counted. Some of these lines are not only gonna, these lines that go out of the surface go out forever. There's going to be now more positive contributions to the flux and less, in comparison, negative flux. And so it's not surprising here that the flux overall should be positive, which is no big deal because, of course, you now trapped inside here is no longer 0 charge. If you add plus 2 and minus q, you still get positive charge enclosed overall. So hopefully I've sort of motivated to you that how much flux you count is how much charge is actually living inside your surface, okay? And the exact relationship, which again, I haven't proven, but I'll try to motivate for you in a second, or in a little bit. I will show that this, when the relationship is exactly like this, it does lead back exactly to Coulomb's law, so that better be the case, because if it wasn't, one of the laws would be wrong, okay? So this relationship right here, this is actually always true, all right? It's the easiest relationship in the world. If you know the enclosed charge, you can get the flux. In fact, this is the easiest thing imaginable. If you can count up how much charge lives in the surface, divide it by this constant, boom, you're done, okay? That's as easy as it is, and there are some homework problems where that's it. If you get given the charge that lives inside, divide by this constant, boom, you're done. That is the flux, okay? And this is always true no matter what. However, there's a catch, okay? This is all well and good, but it could be a complete dead end. We don't really care about flux in it as a quantity that you would want to do anything with. A flux is just a means to an end, okay? So remember, Gauss's law, the only really reason we care about flux is it helps us get to field, okay? So in Gauss's law, the way it works, let me recopy Gauss's law here. Oh, and one thing I forgot to mention, what's this fancy little circle here? This fancy little circle on the integration symbol is just a reminder that the calculation is across a closed surface. So that little circle just reminds us that we want to be integrating across a closed surface. It's just an extra little reminder, although again, Q enclosed would not make any sense with an open surface because you can't trap a charge with an open surface. But that's what that fancy little circle is. This part, being able to know the charge enclosed and just knowing the flux and getting the flux, this part is easy and always true, okay? But this part, getting from the flux to the field, this part, okay, is actually not so easy. Remember, just as a reminder, let me pull it over here. important, Gauss's law is not generally useful if the integration of flux is needed. We want to be able to choose a situation where we can get from flux to field, okay, very quickly. So this actually requires a high degree of symmetry in order to actually do that. And I'll show you those. They're going to be the topic of the next couple videos. There are only 3 symmetries that I'm aware of this Gauss's law is actually practically useful, okay? It's not that it doesn't work all the time, it's just that the integration becomes so brutal you'll probably use the help of a computer. There are only 3 symmetries where you can easily calculate solutions by hand: planar, spherical, and cylindrical. There are more restrictions than that even, which I'll get into. And really, this, okay, is where we get the most use out of Gauss's law. So we can solve things quickly and easily on paper, and I'm going to bounce both of those off in a separate video. The planar one will just go ahead and be like a very quick wet your whistle, kind of see the flavor of Gauss's law. And I'm going to include it on this video only because otherwise the video that would include it is just going to be silly how short it is. So let's go ahead and just knock that one out, and then I'll do the other ones, which are going to form the workhorse of the homework. We'll do those in a separate one. So let's take an infinite plane of charge. Okay. So an infinite plane of charge, we've done this already. And homework number 2, it was quite a journey to get the electric field. Let me remind you how we did this. Before, on homework number 2, what we did was we started with a ring of charge. Then we built, out of a bunch of rings, we built a solid disk. And then we took that solid disk out in all directions until it became an infinite plane. And we finally found that the electric field formula, after all this integration, was, I guess I can just remind you what it was. The electric field is sigma over 2 epsilon naught, okay? I guess it goes out radially. That was quite a bit of work. Let me show you how Gauss's law can do that much more easily. Remember, it's nice to have these 2 tools around. You can do direct integration when you need it, but when it proves to be very, very difficult, Gauss's law might be able to get you there much more quickly. So let me draw an infinite plane of charge. Let's pretend we never figured out what's the field for this, and we just want to do it now. Now, you can, just by just making a few simple arguments, show that the electric field has to be uniform. Okay, and of course it's positive, it's going to have to point away from the plane. So the electric field just looks like that. I already made the argument in a previous video, and when I was talking about the infinite plane, how you could make that argument. Just to recap briefly, if the electric field spread out in either this direction or this direction, kind of either going out along the plane of the page or going out like this, that would be a red flag, because it would seemingly imply that whatever point on the plane that's the field is diverging from would be special, which is weird because every point on this plane is identical. So what it essentially means is that the field can't spread out. And if the field can't spread out, well, it's uniform, okay? So there is a symmetry argument to be made there. And so here is where we write down Gauss's law. So the flux, let me kind of put this off to the side here. The flux is going to be Q enclosed over epsilon naught. And what we're going to do here is we're going to choose the electric field. We're going to choose our surface so that we can use the easy version of the flux calculation. So remember, we have to choose very carefully, okay? Because this part is always true. That's always true. That's no problem. But this, we have to have a symmetric situation. We have to have symmetry. So here's what I'm going to do. I'm going to choose I've heard this called a Gaussian box, Gaussian pillbox, or what have you. But essentially, what this is a surface that is going to it's going to kind of be like a rectangular box, and it's going to include a piece of this infinite plane. I'm not the best artist in the world. Let's just double check here that this is going to look decent. Okay, so this is a rectangular box like so. Okay, and it does include, and I can draw it in here, it does include a small bread slice here of the infinite plane inside it. Okay, now why did I choose that shape? Okay, I chose that shape specifically because it makes my flux calculation easy. So of course my box has 6 sides. So my box has 6 sides. Okay, so the 2 end caps, okay, and then the 1, 2, 3, 4 sides. Okay, that is literally shape of any box. I can use this if you want to see. Okay, so it kind of looks like this. Okay, so you have end cap here, and then 1, 2, 3, 4 sides. Okay, so the normal, let me just pick a normal on this side of the surface, and I want to point out right away that the normal to the top side, okay, so normal to the top side here, the field is pointing to the right, so that's going to be 90 degrees like that. And then you might say, well, what about the part that is of that side that's on the opposite side of the infinite plane? Well, same thing, even though the field is reverse direction over there, it's still 90 degrees. And so the flux there is going to be 0. Well, that argument, by the way, applies to this side. Okay, so if the field points to the right, that's no matter which normal I'm talking about. If it's this one, 90 degrees to the field. This one, still 90 degrees to the field. That's 90 degrees to the field, and even the same thing in the back, okay? So out of the 6 sides, 4 out of 6 sides, the flux is 0 right off the top. That's great, okay? That makes my life easy. And then over here, I pick my normal to this end cap, or I don't pick it. It has to be outward facing normal. Gauss's law already has that baked in. So that one goes like that. And then over here on the back side, like that. Okay, so over here, this side, normal points like this. This side, normal points like this. And there, the angle is 0. So the angle between the normal vector and this rightward facing normal and this rightward field is 0. And then same thing over here. This is leftward normal and leftward field. So 2 out of 6 sides, the other 2, the flux will be plus E. And then I'm going to call, just to not confuse it with the total surface area, which is the capital A, I'm going to call the area of just the end cap little a, and this other end cap is little a as well. So 2 out of 6 sides will get plus E little a. So remember, the cosine of 0 went to plus 1, right? So 2 out of those 6 sides, we got the electric field is uniform, nicely behaved, doesn't change its strength, it doesn't change its direction. It's nicely behaved across this entire end cap. And so my overall flux is going to be that times 2, right? I have 2 end caps, okay? So that's my flux. And if you look at that, that's a simple relationship. The flux can be easily related to the field. That's this part. But I had to very, very carefully pick a Gaussian surface that would make that possible, okay? You would not, for instance, just as a counterexample, if I picked this, or if I had an infinite plane and the field looked like this, you would definitely not want to choose, for instance, a spherical Gaussian surface. That would be a nightmare because the normal is going to keep changing how it orients to that field. Even though the field itself is nice and well behaved, it's uniform, it's not nice and well behaved relative to the normal. So that would not be a wise choice, okay? That would be a very bad choice of Gaussian surface because you are not getting the symmetry you need. You would have to do the integral form E dot dA, and if you're doing that, you're going off the wrong path. Stop and don't do that. Gauss's law is not useful for that sort of thing, at least on pen and paper. Okay, so now let's get to this part. We've already gotten this part done, okay? How much charge do we actually have enclosed? So this is where it's really important to remember it's the amount of charge that lives inside the Gaussian surface. There is a bunch of charge, in fact, an infinite plane of charge that is outside, but how much charge is really on this little bread slice that I've cut out? Okay, that is my enclosed charge, that blue slice here. And I know I draw my infinite planes looking like slices too, but do remember that that goes out. But this is just a slice, okay? Now, how much is in there? Well, the Q enclosed. Let's say we know that the charge density, sigma, well, if that's true for the whole plane, that's true for this slice. And then how big is this slice? Well, that's going to be determined by the size of my catcher. My Gaussian surface was this rectangular box, and that's what created this slice. So that slice is actually size A as well, the little a, right? So we have two end caps of area A catching the field made by a single slice inside, which is of area A. Okay, so now let's put it all together, okay? So we know that the flux on one hand, remember the flux is just the middleman, flux on one hand tells us the relationship between flux and fields, so that's EA, and I'll put the 2 in the front, right there. Over here, I'll put in the Q enclosed, sigma A. The A's cancel. Oh, and I forgot, whoops, don't forget my friend divided by epsilon naught. A's cancel, and I get my electric field is sigma over 2 epsilon naught, which is correct. And what I got before, I would imagine you would say this is far easier to do than what we did before to get it. So you can see Gauss's law is very, very good when it works, when you have a highly symmetric situation. Now, one thing I do want to point out, the A canceled, which is good. And the reason why it's good is because A, okay, is an arbitrary property of my Gaussian surface. It's something that I chose to sample my field with. It should not end up in the answer. It would be really weird if it ended up in the answer. Because here's the thing, Gauss's law is a tool, okay? Gauss's law is a tool. After we're done using our tool, we clean up, okay? If you bought a brand new house, you'd be really upset if someone left hammers and saws all over the floor when you moved in, okay? So Gauss's law comes in, it puts this surface in here, and it simply uses it as a tool to relate the charge and the field. This box is our tool, and it would be really weird if the end result of how strong the electric field was related to the tool we used to measure it, okay? Ultimately, this charge distribution exists. It's a sigma infinite plane, and it makes a field whether or not we're coming around to use Gauss's law or anything to determine that field. The Gauss's law is just a tool, so we put this box in here to sample it and relate the charge to the field, but afterwards we clean up after ourselves. There should be A is an arbitrary property of the Gaussian surface. It should not end up in the relationship between the charge and the field that it makes, okay? That would be strange, okay? So that's a little flavor of how, what Gauss's law is, the theory of it, a little flavor of how it works functionally. Of course, we didn't really need Gauss's law to get us this field. We already knew it. And that's about as far as I can think of in terms of like what you can do with the planar symmetry. Again, remember that this really comes into its own and shines when you get to the spherical and cylindrical symmetry, where you can find fields of charge distributions that we would not have touched before that are three-dimensional. You can do that relatively easily. So I'll talk about that in the next video.